So continuing on test design, we're going to take a look at what's often called control flow testing, although some people might call it path analysis. It's a type of test design which can be applied anytime that you can represent the testing problem with a control flow diagram or basically any directed graph. So that's the type of thing we're doing. We're looking at a sort of a network of objects and finding pathways through them. So this is control flow testing. The paths through a system can be meaningful for many different ways. It could be the flow that data takes through a system, the flow that a transaction takes through a system, the flow the code goes through. We can model the code and look at control flow of code, and a lot of people do that. And we can also look at processes, both business processes and actually technical processes running on computer systems. The idea is to basically have a network with a lot of possible paths. We can't test all of them. How do we find a reasonable subset to test to thoroughly exercise the part of the system that we're interested in studying? So this is when there's usually something large number of possible paths, maybe an infinite number of possible paths, and we don't really have the time or the budget to go anywhere near testing that much. So how do we find a reasonable subset that can thoroughly exercise the system under test? So the first step is to model the system with a control flow diagram. The control flow diagrams are circles and arrows and not too tricky to draw. They're very similar to flow charts. They look a little bit like state models, except they're sequential, not stateful. So here we have to create a control flow diagram. And once we've got the diagram, then we find pathways through the diagram. And the set that's really interesting is a set that was sort of identified and described a lot by a guy called, let's see, the cyclomatic complexity was first developed in Chicago, cyclomatic complexity. And the guy who published on it, let me just check his name out here. Cyclomatic complexity. The chap who came up with it is Thomas McCabe. So they call it McCabe's cyclomatic complexity. And basically, McCabe studied directed graphs, usually ones that represented code, and he found an interesting set of paths called the basis path. And it's a subset of all the pathways through the system that if you exercise the set of the basis paths, you will have exercised each step at least once, each decision outcome, every way it can go at least once, and you can have confidence that any combination of these paths can create, any path can be created by a linear combination of the paths that you've tested. And I'm not sure exactly how linear combinations of paths works, but I have used for many years the work of McCabe. It has helped me, and it can give you a really good set of paths to exercise, so you have sort of confidence that the system as a whole is relatively robust. It's not testing every path. There are still risks in there, outliers, strange situations that may occur, but the paths that you test are the paths that I think have a certain realism to them. So this is the basis paths. It's a subset that's found, and the algorithm for doing it I'll describe a little bit in here. But to look at the research and the discrete math behind it, you'd want to look at the work of Thomas J. McCabe Sr., published as early as 1976, used in many white box testing tools, and also famous for computing what's called the cyclomatic complexity, which is the count of the number of basis paths in a piece of code. To draw a control flow diagram, well, we can start by looking at process steps and put them in nodes or circles. So step A flows to step B flows to step C. That's process steps. We can also add to that a looping construct where A flows to B flows to C, and C loops back to A. We're allowed to do that. There's no rules or restrictions on it as long as they're directional. It's a directed graph. We can have decisions. We usually represent them with the notation like this, where A flows to C or B. Convention has it that true is on the right, but it doesn't really matter. which way you do. If you're consistent, that's good, but A flows to C or A flows to B. And similarly, we have junctions. So C comes from A or C comes from B. So that's a junction. So we have steps in sequence, including looping, decisions, or junctions. There's not too many concepts there. There's 3 constructs there. And if we can take an object, a piece of code, a network, and draw a control flow diagram of it, then we can actually just look at that picture and compute the number of basis paths. And this is comes from some basic equations in discrete math. An easy way to do it is to look at the enclosed regions and add 1. Count the number of enclosed regions and as 1. So this one has 1, 2 enclosed regions plus 1. Therefore, there's 3 basis paths. But McCabe made this cute little equation here, which said that P, which is the number of basis paths, is equal to E minus N plus 2, where E is the number of edges, N is the number of nodes, and 2 is just a constant here. So if I take this picture here and I look at it, we have 9 nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So P, the number of basis paths, or the cyclomatic complexity, is 10 minus 9 plus 2, which is 3. And of course, McCabe gets into fancier calculations of this when he has situations which he calls disconnected graphs and all sorts of things like that. So for me, most of the graphs I work with are connected graphs with many, many nodes and many, many edges, but they can all be drawn on a, basically a sheet of paper here. And it's, fairly interesting to do that. The basis paths, well, this is one set of them. There's more than one solution to the problem, but this is one set. So if you try to follow this A, B, D, E, G, H, I, that's one path. And then I do A, B, C, E, G, H, I, that's a second path. And then the third path would be A, B, D, E, and then we've got F, H, I. And that's the third path. Those 3 make up the basis paths of the set. And if you exercise these paths, you'll have exercised every step at least once, every edge at least once, and according to McCabe, you can create any path by somehow combining these paths. So you have confidence that the connectivity of the flow is useful, the transactions are going the right place. You might not know if the calculation on every step is perfect, but you've exercised very thoroughly the pathways through the system. So you can expose basically a lot of bugs which are cross-feature independence. There's bugs that happen, if A happens and B and D might be different from A, B, C. So there's order dependencies, there's cross-feature interference. Maybe B interferes with C, but not D. So if the path goes through D, you'll never find the bug that's injected in C, etc. There's path dependencies in bugs and software sometimes. If they share objects and data and code, it's more likely. The basic algorithm that I learned to find basis paths by hand is I take this from, although it's from McCabe's work directly, I'm quoting it from Lee Copeland's book, A Practitioner's Guide to Test Design, who has a nice chapter on control flow testing. And the basic algorithm is like this. You start, and you basically start with what he calls a typical baseline. So you take a common path, a typical path through the system, and that's going to be your first one. That's the one Lee wants you to start with. Actually, you can start with any path, but Lee suggests start with the typical path. And that gives you your first path. Then, to find the second path, you flip the first decision in the first path, but keep the rest as close as possible to the original path, Then you go down and you continue to the third decision until you've exhausted all the decisions in the first path. Then you pop the second path off the stack and look at the next decision in that path and flip the ones until you've exhausted all of the paths. It's sort of a recursive algorithm, but after you've gone through it and exhausted them all, you've actually built a set of basis paths. Doing this by hand is very painful, very tedious. So for larger solutions with several paths through it, I urge you to use tools. There's a tool that was put together by actually McGill students several years ago in one of the project teams that we were working on. and I'll put a copy of that, the module paths somewhere in the my courses there if you want to use that for larger systems. It's not a very robust piece of software, but it does the job of finding paths, and I've used it a lot in my career. So here's an example. Let's say you have this little flow chart for keyword optimization. So you'll see it's a flow chart. It's not a control flow diagram. So the first step is to try to create a control flow diagram, which I do by this diagram here. So first I label all of the steps, or all the steps in the flow chart here. I label them. I try to give them short labels, which are basically 1 or 2 letters each. And this is helpful for me when I use that paths tool, which is not terribly robust, but it seems to work better if you have short strings for the path name or for the names of the nodes. And then I basically drew it as more of a control flow diagram. If you'll see, A goes to E here, A goes to B, B goes to G, B goes to C, C goes to D, G goes to H, F goes to G, etc. So this is basically a control flow diagram representing that flow chart. There's 11 nodes, there's 14 edges, therefore there's 14 minus 11 plus 2, which is 5, so there's 5 basis paths. Also there's 4 enclosed regions plus 1, which makes 5 basis paths. And to find them, you might apply that algorithm and come up with these 5 paths, I think is the set. And if you draw them with my ugly skills here, these are 5 paths through the system: the yellow pass, the red pass, the blue pass, the green pass, and the orange one here. So those would be the basis paths through the system. If you test at least one test for each of the basis paths, you'll have thoroughly exercised the control flow of this system. When I talk about some philosophy, early on in the course, we looked at some philosophy. I shared an example from an insurance company, and this example was actually a control flow testing example, which was solved with the mechanism of drawing a control flow diagram. So if you recall, there was 3 controls. Each control interacted with other controls to go to unique pages. So we had it for A, there were 5 choices, B, there were 6 choices, C, there were 2 choices. Each combination of A, B, C went to a different page. So therefore there's 5 times 6 times 2. That made 60 choices. And so the customer had very thoroughly tested all 60 functional areas of the system, all 60 pages of the system, but they were still running into tons and tons of problems. So they wanted to test all the permutations of that, and the number of tests to test all the permutations of 60 objects would be something in the order of 8.32 times 10 to the 81, which is more than the number of atoms in the visible universe from Hubble, according to NASA. So this is ridiculous, this is crazy, this is intractable. There's no way anybody could or would want to test that much, no matter how much automation you have. This is absurd. And so I went and I asked them if they had any idea of the workflow around the system. And workflow is something that can often be modeled with control flow diagrams. I discovered the workflow of the system. I talked to people who worked in the training department and the help desk department. They got me the information. I took the flow charts of the system. I interviewed the various stakeholders to learn what they meant. And then I basically created by hand this control flow diagram. It's a little bit ugly, but it's plainer. It was easy to track. There were 45 nodes, 65 edges, giving a cyclomatic complexity of 22. It's interesting to note also that even though the system had 60 pages, there were actually only 45 of them that showed up in workflow. So there's 15 pages in the system that don't show up in any of the workflows people are supposed to use. Found that a bit intriguing. But nonetheless, with this, I then applied the algorithm, Lee's algorithm, by hand as best as I could. And I came up with these 22 test cases. So walking through these are the names of the nodes. The customer was able to take these 22 test cases, and it took about 3 weeks to do. They had to set up transactions and transaction data to go through each of these paths. And when they went through the paths, of course, they exposed great bugs because there was cross-feature interference all over the place. They found the bugs, they fixed the bugs, they continued, they resumed. And by the end of about 3 weeks, they were able to go through easily all 22 paths cleanly without any problems. And subsequent to this, we're able to go to live production operation with no further software engineering changes. So I like to suggest that this type of analysis is a very powerful way to ferret out bugs related to the interference of one feature with another feature on a system. So cross-feature interference, which shows up when features share data, share objects, share methods, share class, even just share memory and processing, can be ferreted out with this type of test design. Other interesting tests that you might look for if you've got a control flow diagram is tests which exercise maybe the set of tests that exercise every node at least once, or the test that exercises every edge at least once. Or if you don't have looping, you can consider the test that exercises all paths at least once. And if you have looping, that might be infinite. So you have to be very careful about the all paths case. So over and above the basis paths, these may be interesting paths to test in your control flow diagram that may make sense given your project. The tool that I'm talking about here, called Paths, has as its input a text file, which is an edge list. It's a text file. The first line is the name of the first node. You'll notice I use short strings. I try not to include special characters in there. I try to use like just simple uppercase characters and numbers, starting always with a letter. And so, for example, the first node in this diagram here on top is start. The last node is end. So the first line of the list is start. The last line of the list is end. And then the first edge goes from start to A, then A to B, A to B, B to D, D to A, B to C, C to end, and the last one is end. So start to end, and those are the edges. So the edges are just written on a line, simple text file, name of the start node, name of the end node for each edge. That gives you the edge list. Then you run the tool, which is just a Java application. So it's usually done through a batch file. It's a Java jar. And you would get an output like this, which for the basis paths, in this case, would give us 2 basis paths. And also I ran it just to find all the edge paths, and it found this path would exercise all the edges. So the basis paths a little more thorough. In this little example, we find only 2 test cases there. We may as well do them. It's not that complicated a system. However, it's fun to sort of say that there's simple tools that can really facilitate some pretty complex analysis. Of course, there's also tons of tools that do white box test design, notably from a company called Parasoft. They make a lot of tools like this that will analyze your code, and they will identify a set of tests which will actually exercise all of the basis paths. And then they will also, while you're testing, do coverage analysis dynamically to see if you're exercising all these paths in the instrumented code. And yeah, that's it for control flow testing. Thank you very much.